Theorem 5.2. If n is odd pseudo-prime, then m sub n equals 2n minus 1 is a larger one. We can agree with this because n is a composite number. We can write n equals r times s with r greater than 1 but less than or equal to s, which is also less than n. So this means that integer r and s is greater than 1. Then according to problem 21, section 2.3, r raised to the power of r minus 1 divided by 2 raised to the power of n minus 1, or equivalently 2 raised to the power of n minus 2 equal kn for some integer k. It follows that 2 raised to the power of m sub n minus 1 equals 2 raised to the power of 2 sub n minus 2 equals 2 raised to the power of k sub n. This yields 2 raised to the power of n sub n minus 1 equals 2 raised to the power of k sub n minus 1. Yeah, process equals 2 raised to the power of n minus 1 times 2 raised to the power of n times k minus 1 plus 2 raised to the power of n times k minus 2 plus and so on plus 2 raised to the power of n plus 1 equals m sub n times 2 raised to the power of n times k minus 1 plus 2 raised to the power of n k minus 2 plus so on and 2 raised to the power of n plus 1. So the answer is 0 modulo of n sub n. We see immediately that 2 raised to the power of n sub 2 minus 2 is congruent to 0 modulo m sub n, in light which m sub n is a pseudo-prime. More generally, a composite integer n for which a raised to the power of n is congruent to a modulo of n is called a pseudo-prime to the base a. When a is equal to 2, n is simply said to be a pseudo-prime. For instance, 91 is the smallest pseudo-prime to base 3, whereas 217 is the smallest such to base 5. It has been proved 1903 that there are indefinitely many pseudo-primes to any given base. Theorem 5.2. These prime impostors are much rarer than our actual primes. Indeed, there are only 247 pseudo-primes smaller than 1 million in comparisons with 78,498 primes. The first example of an even pseudo-prime, namely the number 161,038, is equal to 2 times 73 times 1,103. This is only equal to 161,038. This was found in 1950. There exist composite numbers n that are pseudo-primes to every base e, that is, a raised to the power of n minus 1 equals 1 modulo of n. For all integers a with GCD of a and n equals to 1. The least such is 561. These exceptional numbers are called absolutely pseudo-primes or Carmichael numbers. For R.D. Carmichael, who was the first to notice their existence. In his first paper on the subject, published in 1910, Carmichael indicated 4 absolute pseudo-primes, including the well-known 561 equals to 3 times 11 times 17. The others are 1105 equals to 5 times 13 times 17, and 2821 is equal to 7 times 13, 31, and 15,541 equals to 7 times 31 times 73. 2 years later, he presented 11 more, having 3 prime factors, and discovered 1 absolute pseudo-prime with 4 factors, Specifically, 16,046,041 equals to 13 times 37 times 73 times 457. To see that 561 is equal to 3 times 11 times 17 must be an absolute pseudo-prime. Notice that GCD is A and 561 equals gives. GCD of A and 3 is equal to GCD A and 11 equal to GCD A and 17 equals 1. An application of Fermat's theorem leads to the congruences A raised to the power of 2 A squared is congruent to 1 modulo of 11. A raised to the power of 10 is congruent to 1 modulo 11. A raised to the power of 16 is congruent to 1 modulo of 17. And in turn to A raised to the power of 560 congruent to A squared, which is raised to the power of 280 congruent to 1 modulo of 3. A raised to the power of 560 congruent to A raised to the power of 10, which is raised to the power of 56 congruent to 1 modulo 11. A raised to the power of 560 congruent to A raised to the power of 16, which is raised to the power of 35 congruent to 1 modulo 17. These give rise to the single congruences A raised to the power of 560 congruence 1 modulo 561, where GCD A and 561 is equal to 1. But then, A raised to the power of 561 is congruent to A modulo of 561 for all A, showing 561 to be an absolute pseudo-prime. Any absolute pseudo-prime is square-free. This is easy to prove. Suppose that A raised to the power of n congruent to A modulo of n for every integer A, but k raised to the power of 2 divided by n for some k greater than 1. If we let A equals k, then k raised to the power of n is congruent to k modulo of n. Because k raised to the power of n divided by n, this last congruence holds modulo k squared, that is k congruent to k raised to the power of n is congruent to 0 modulo k squared, whereas k2 divided by k, which is impossible. Thus, n must be square-free. Next, we present a theorem that furnishes a means for producing absolute pseudo-primes. So now let us proceed to Theorem 5.3. Let n be a composite square-free integer, say n equals p sub 1, p sub 2, and so on p sub r, where the p sub I are distinct primes. If p sub I minus 1 divided by n minus 1 for I equals 1, 2, and so on r, then n is an absolute pseudo-prime. The proof for this is, suppose that A is an integer satisfying GCD A and n is equal to 1, so that GCD A and P sub I is equal to 1 for each I. Then Fermat's theorem yields P sub I divided by A raised to the power of pi minus 1 from the divisibility hypothesis P sub I minus 1 divided by n minus 1, we have P sub I divided by A raised to the power of n minus 1 minus 1. We have P sub I divided by A raised to the power of n minus 1 and minus 1, and therefore P sub I divided by A raised to the power of n minus A for all A, and I is equal to 1, 2, 3, and so on r. As a result of corollary 2 to theorem 2.4, we end up with n divided by a raised to the power of n minus a, which makes n an absolute pseudo-prime. Examples of integers that satisfy the conditions of theorem 5.3 are 1729 is equal to 7 times 13 times 19, 6601 equals 7 times 23 times 41. Another example is 10,585 is equal to 5 times 29 times 73. It was proven in 1994 that infinitely many absolute pseudoprimes exist, but that they are fairly rare. There are just 43 of them, less than 1 million, and 105,212 less than 10 raised to the power of 15.